Okay, back to our lectures. We're going to discuss now interrupts, and we're going to finish chapter 6 today. It's been a long time since we last met. Interrupts. Interrupts look like subroutines, but they differ in the way they are called and in the way they return. But look like subroutines because they are short programs to perform some tasks. And subroutines are generated only by software. You call a subroutine and come back from a subroutine through a software. But interrupts can be generated, called and returned from through hardware as well as software. So an interrupt can be hardware generated from some external device or peripheral, and as well can be software generated through your code. We call this internally derived. And what interrupts does, it similar to subroutine, stops the currently being executed program and goes to some specific address to run a code to perform a specific task. So they have calls, but different from the way we call subroutines. So they have special types of code. This is regarding the Intel's processor 8086, 8088. In calling interrupt, we should specify what's known by an interrupt vector. So ISRs, or interrupt service routines, are called by some interrupt vectors. Interrupt vectors, these are, each vector contains 4 bytes of memory in which we store IP and CS, the values to be placed in IP and the values to be placed in CS. So we have to read from memory 4 bytes, 4 memory locations, 2 of which should be used to modify the value inside CS to indicate which code memory segment has this specific interrupt service routine, and the other 2 bytes of memory we read and store them or modify the value inside your IP. So now you know which interrupt service routine to start run by modifying the values inside your CS and the value inside your IP. Okay, so this is why system designers reserve the first 1024 bytes of your memory. We have 1 megabytes of memory. The first 1K bytes are used to store your interrupt vectors. So from address 0 to address 3FF. So these are addresses used to store interrupt vectors in. And we said that each interrupt vector requires 4 bytes. So this 1024 bytes, if you divide them by 4, you will get 256 vectors, meaning your system can take up to 256 interrupt service routines. So you can design a system which contains at most 256 subroutines, store their addresses into the first 1K bytes of memory. So you have 256 interrupt vectors. These vectors refer to interrupts that can again be called from a hardware device or through your software. Each vector contains the address of the interrupt service routine that is to be used, to be called. Again, as we said, the first 2 bytes of the vectors contains the number that is loaded into IP. So the value to be placed in your IP are read from the first 2 bytes. And the value to be placed in your CS are taken from the next 2 bytes. So the interrupt vector tells you where to go regarding the code memory segment and where to start at this specific code memory segment. Okay, here is a schematic for the interrupt vector table. So this is the first 1 megabytes of memory, and the interrupt service routines are enumerated: ISR 0, interrupt service routine 1, up to interrupt service routine 255. So all in all, we have 256 interrupt vectors. For example, if you are to call the interrupt service routine number 0, you would have to go to the first 4 bytes in your memory, byte number 0 and byte number 1. You get a value 16 bits to be placed in your IB. So this is the value of your instruction pointer. And the next 2 bytes, byte number 2 and byte number 3, you get 16 bytes from to modify the value inside your code segment register. So now you can start running your ISR 0, and you do the same if you are calling ISR 1, ISR 2, and so on. Okay, good. So the interrupt vectors, the 256 vectors, are mapped or distributed as such. The first 5 vectors are already written for you. So written for you. ISR 0 is already written and indicates divide error. So whenever you try to divide in a mathematical operation by 0, this interrupt service routine is called and will give you a message warning you that a try is being done to divide by a 0. And the interrupt service routine number 1 is already written for you for single stepping. So you call this interrupt service routine number 1 when you need to go and locate some error. When you debug your program, you have to go for this mode, single stepping mode. And again, this is interrupt service routine number 2, which is non-maskable interrupt. In hardware interrupts, we have maskable interrupt, so an interrupt service routine that can be rejected or can be waited, and a non-maskable interrupt, an interrupt service routine that has to be called and run immediately. We cannot wait, or we cannot wait for calling this, and this cannot be rejected, the interrupt service routine, which is non-maskable interrupt. So a non-maskable interrupt cannot be rejected, while maskable interrupt can. Okay, can be rejected. Good. So for interrupt vectors number 5 to number 31, these are reserved by your system designers for future use, and we'll see in a moment how could we use these interrupt vectors. You as a user can generate as many interrupts as you wish when you design your system, but you have to stick to interrupt vector number 32 up to 255. So this is the range of interrupt vectors you can use as a user. The beginning address is this, and this is your final address, and you can define as many interrupts as you wish within this range. Okay, here again, this is the first 5 interrupts already written for you in 80, 86, 80, 88 microprocessor based systems, and as a matter of fact they are used by all Intel's processors. Divide by zero, single stepping, non-maskable interrupt, breakpoints, interrupt on an overflow, and in 186 they added one more interrupt service routine using interrupt vector number 5 for bound instructions, and they did similar things for different microprocessors, and we have here up to Pentium Pro, Pentium Professional. So they used interrupt vector number 12 for Pentium Professional to store an interrupt service routine which is used for machine check exception. Again, the rest of the first 32 vectors are still reserved by your system designers for future use, and you are again allowed to use vectors from vector number 20 to FF, addresses from 80 to 3FF, and you can generate and design as many interrupt service routines and this range can take. Now we'll talk about interrupt instructions. There are 3 different interrupt instructions available for the programmer. Alright, these are int O, and int3. Okay, int is a software interrupt call. So you call a software interrupt by int, but you have to provide the number of an interrupt vector. Alright, so you call int, for example, int 50. You, as a designer, have written an interrupt service routine. We call it ISR 50, and you placed the address of this specific subroutine into your memory, and you have to call the vector inside your memory, which is the 50th vector, to go to this IRS 50 and start executing it. So you can call this by typing in your code int 50. So you have to follow int by a number. While this int O, when you write this in your code, int O, meaning interrupt over an overflow. So whenever an overflow takes place, you go and execute this specific interrupt service routine to warn you as a user, as a programmer, that there is a number generated that your destination cannot take, whether your destination is a memory location or a register. While here, this is the interrupt ISR3. So the interrupt vector used is a special interrupt service routine enumerated 3. Okay, so again, this int, you have to follow this int by some interrupt vector number from 0 to 255. Okay, and each instruction, interrupt instruction, is 2 bytes long, except for N3. N3 is a 1 byte long interrupt instruction. Okay, and again, software interrupt instruction is N. You have to include this if you are to call some interrupt service routine by your software. You use this instruction int followed by your interrupt vector number. Okay, and what this interrupt does is the following steps. First, it pushes your flags into the stack. So whatever your flag bits are, they are going to be stored into the stack. Then it will clear the I interrupt flag bit and the trap flag bits, because this int is called by indicating that an interrupt is to be served and your code has to be stopped, as if you are trapping your code. So these two bits should be set before your interrupt. This is why your interrupt call will clear these two bits. Okay, and stores the interrupt call will store your CS into the stack to know where to go when it comes back from an interrupt. So your currently CS should be stored in the stack, and your new CS from your interrupt vector, all right, from your interrupt vector, you go to the memory and get 16 bits to fill CS with to know your new code segment, code memory segment. And you do this with your IP. First, you place the current IP into the stack. Next, you go to your memory by the help of your interrupt vector to get your 16 bits to know your new IP. So now your old CS and IP are stored in the stack, and your new CS and IP are obtained from memory by the help of the interrupt vector. Then you go to this new location, CS and IB, and start serve or handle your interrupt service routine. Okay. Now N3, which is 1 byte long instruction, what it does, it gives you the ability to set a breakpoint inside your code. So if you need your code to run and stop at very specific location to check whether the code is correct or not, you can use N3 by which places a breakpoint whenever you write N3 into your program. This is why it is a special interrupt instruction and can be put anywhere in your code. This is why it's made to be a 1 byte long, so can be easily squeezed inside your code. And when you issue this interrupt instruction N3, what it does, it makes your code stops and it displays for you all register values and waits for you to decide what should be done next. This is a good way to debug a faulty program, to locate an error inside your code. Int O is an interrupt instructions, and it's a good habit to use it from time to time, because it assures you that whatever numbers generated from your code can be safely stored in your destination. Okay. So from time to time you should check your overflow flag bit to see whether it's raised or not, and when you place int O inside your code, alright, it will warn you and give you a message whenever an overflow takes place. So it always looks for an overflow error. And this overflow usually appears after arithmetic operations, if you add or subtract. Each interrupt service routine should be ended with IRET instruction, interrupt return instruction, and it does the image, the opposite of int, of the interrupt call. So it pops up your IP from the stack, your CS from the stack, so it knows where it goes to your main code, and the flags are now returned back to their flag registers. And the values of your IF and TF are restored. So now let's take an example to know how software interrupts are generated. Now we need to write a code for some interrupt service routine, and the code is to add the value of your DI to the value of your SI to the value of your BP to the value of your BX. So we need, and save the result in AX. We need to add, sum up the values of DI, SI, BP, and BX, and the result should be saved in AX. And whenever you need this interrupt service routine to be called, which means whenever you need to add the values of DI, SI, BP, and BX and store this into AX, you call this subroutine by this instruction, int 50. You give the vector, the interrupt vector, number 50, which means what? Number 50 multiplied by 4, because each interrupt vector requires 4 bytes. 50 times 4 gives you 200. So you write your code, and when you write your code, you know where you wrote it, which means you know your CS and IP, and you need to call this code by this instruction int50. This is why 50 times 4 gives you 200. So in memory locations addressed by 200 and 201, you place your IP. 202 and 203, you place your CS. If you did so, whenever you issue int50 in your code, it will go and get this IP and CS from the memory and start executing your ISR. For example, add them. Now BX is added to AX. SI is added to whatever value inside your AX. DI is added to your AX. BP is added to the value inside your. So now we added the values of the 4 registers into your AX. Done. Okay. End your code with the interrupt return instruction. Okay. You know definitely where you wrote this code. You know definitely your CS and IP. What you do, you have to originate your code in this memory location, all right, and place your IP in address 200, 201, place your CS in address 202, 203. Okay, good. Regarding hardware interruption, if a device, a peripheral, let it be, for example, the printer, needs to receive some data from system to print it out, and it needs to inform your system that it is ready to receive new data. Okay, so you're running some code and you're sending some data to be printed out. Once your printer finished printing out the received data, it informs the system that the printed out data is available and it's ready for a new printout. So what the printer does is this sets the interrupt flag bit to warn the system that a hardware interruption is being sent. And when it's done, it clears this interrupt flag bit. So whenever your interrupt flag bit is 0, your int R, this is the hardware interrupt instruction, is disabled. So no hardware interrupt service routine is to be served. If you need an interrupt service routine to be served, your peripheral should set the interrupt flag bit to 1, then your interrupt instruction is enabled. Okay, so your system knows now that an interrupt service routine is to be executed depending on the call from some peripheral. So what is calling the interrupt service routine is some device hooked to your system or some peripheral, all right? So what this device does is setting your IF, and your system will enable your interrupt pin, INTR pin will be enabled. Then the address of the interrupt service routine to be operated is fed through your control unit. So now an interrupt is called by hardware, the address is provided by your control unit, so your system will stop the currently being executed code and handle this interrupt service routine. All right. So let's now talk about some miscellaneous instructions. By miscellaneous instruction, these instructions help a programmer to control the codes. So they are not specified as logic instructions, arithmetic instructions, or even program control instructions. Additional instructions for user to ease his life in programming the system. And most of these instructions are used in hardware control, and they include the carry flag bit. They control the carry flag bit, the wait instruction, the wait instruction. This is a very important instruction because usually your microprocessor runs much faster than the memory can be accessed. So if you're connecting memory to your microprocessor, sometimes the memory cannot handle data as fast as your microprocessor. So you ask your microprocessor to wait for a while till your memory can be read or can be written into. This is why we have this. So whenever you connect or interface a slow memory to your processor, you would use this wait pin. Halt stops your code for some reason you know of. NUP, this is no operation. You can issue this NUP whenever you need to delay your program for a while, and this delays your program for 3 clock cycles. Lock prefix, if you need to skip some instruction from being executed, you prefix it by this phrase, lock, L-O-C-K. And escape makes your system leaves the code which is running and pays attention to what you need to do. Okay, so this is wait. So it tests the hardware pin. All right. If the pin is 1, okay, so the wait is activated now. Your system will become idle till the wait becomes a 0 again. So it will wait for some time till a 0 is sent to this wait. Halt stops the software being executed, and you can do this by interrupt or you reset your system. No operation, it takes 3 clock cycles for your for your system to get delayed. So whenever this NUP is executed, is handled, your system will do nothing through 3 clock cycles. Then will resume execution. and it is usually used to delay your software. And it is always said it's a good habit for you as a programmer, if you're writing a system, designing a system using software, from time to time you leave a patch of 50 bytes in several locations inside your code. So these 50 bytes will enable you to modify and debug your code if needed. So you don't have to rewrite the code from the very beginning by leaving empty patches of 50 bytes in several locations. So lock prefix, you place it before any instruction if you want this instruction to be skipped, if you don't want your system to execute this instruction. Escape, this deals with external processor. So you escape when you issue this instruction. It gives control to an arithmetic coprocessor. So it leaves the main processor to the math coprocessor. Again, in early processors, to enhance the power of the processor in doing arithmetic operations, they designed a processor specifically for these arithmetic operations, and it is used with the main processor. This is why it's called co-processor, and is dedicated only for arithmetic operations. So if you have some arithmetic problems, some rigorous arithmetic operations, you may instruct your system to leave the main processor and go to the math coprocessor to enable you to perform these rigorous operations by escaping. While your main processor will execute NUP, will do nothing. And the memory control, read and write, is now passed to your coprocessor. Okay, this is an example of an interrupt service routine. As a matter of fact, this routine is presented by Barry Bray, the author of the book we're using, and through which he wrote his name. I copied it I wrote my name, Muhammad Banna. Okay. In order to explain the way data are sent to your screen, this is an external device, and being printed. Okay, this instruction 6 equals 6. And instead of writing 6 this way each time, we can write it SIX. Okay, when you place 6 into your AH, first place 6 into your AX. Then inside the L, you write the ASCII code of the letter you need to print out. Then you call an interrupt service routine, the 21st interrupt service routine, by issuing interrupt 21. All right, so AH now is loaded with a 6. DL loaded with the ASCII code of the letter you need to print out, then int 21 will print out this letter M, which means int 21 can do many things, one of which is to print whatever value inside whatever ASCII code inside your DL if you place 6 in AH. This is why you need to print or display the O. You place your O in DL and you issue int 21. If you need to display letter lowercase h, you place your h in DL and you issue int 21. As long as the AH contains 6, int 21 will go to your DL register, get the ASCII code from, and display it. Alright, so now we've finished chapter number 6. We'll see you shortly in chapter number 1 in the hardware portion, which is 7 here. Okay, again, lectures are given numbers according to the week. So you have now lecture number 6 for week 6, the 3 hours, lecture number 7 for week 7, and we have 1 week off, and this is lecture number 8 for the week number 8, and other lectures are to be presented to you for weeks 9, 10, 11, at most 12 or 13 lectures. Thank you.